Today we're going to be predicting from raw data. So that means we're going to be doing this whole prediction thing that we've been doing, but we want to be focusing on doing it from data that's not even written in a table. So let's have a look at it. So the data gives the latitude in degrees south of a number of Australian cities, followed by the average minimum temperature degrees Celsius for February. So you've got Adelaide, Alice Springs, Brisbane, Canberra, Hobart, Melbourne, and Perth. And just so that we're really clear, the first value is the latitude. So latitude, 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 and the others are all the temperature. So temperature, 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 so on and so forth. Okay, so just so that we're really clear, that's what the data, and then that's the way it's been produced. We don't tend to see data written like this, so I'm just going to quickly turn this into a table. So I'm going to write my draw up my table, and we're going to do that quickly. Alrighty, so I've set up my latitude and temperature table, and I believe that latitude is the explanatory variable, because I would imagine that the further south that you go, the colder the temperature would be. So as you go further south, as south gets increased, then the temperature should decrease, right? Because the South Pole, Antarctica, is quite cold, whereas near the equator, Northern Australia, or anywhere around there, you're going to find that it's a lot hotter. An easy way to think about it is that, is it hotter in Cairns or in Antarctica? The answer is that it's hotter in Cairns. Alrighty, so let's just put in the data. So the first one's for Adelaide, so it has 34.9 for the latitude, and the temperature is 28.5. And I'm just going to quickly do that for each of the cities. Alrighty, so there's all my data done, and now I can quickly do up a scatter plot. And so on my X is going to be the the explanatory variable, so it's going to be my latitude, and on the Y variable axis, I'm going to have my temperature. Alrighty, I'm going to set up my axes and start plotting. Now I'm going to use a double Z here. I think that it makes no sense to start all of the numbers at 0 when you can see that all of the data is really in the 20s and 30s and 40s for the latitude. So let's go set up numbers. My smallest number for my latitude is 23, so I'm going to start at 20. And my temperature's lowest value is 21. So once again, I'm going to start at 20. So after playing around with my axes for a bit, I've decided to go up in 3s. So each of these dashes is 3 on. Obviously you could do 5, or you could do 10, or you could do whatever. But in this case, I just found for the spacing that I've got, that going up in 3s looks quite nice. So the major ones are going up in 6s, but each of those dashes is a 3 higher than the previous one. Alrighty, so now I can go through and actually plot all the points. So the first one is 34.9, which is about 35, which is about here, and 23.7. So there's my first point, and now I'm just going to go through and do all of the points. Alrighty, so I've plotted all the points, and now I can move on to the next part. So that's part A all done. Oh, sorry, and I've got to determine the least squares equation and the correlation coefficient. So the next thing I want to do is to get my line of best fit. And I'm going to use my calculator to do all of this. So I'm just going to type, this is my X, this is my Y, and I'm going to work at A, B, and R from my calculator, and then I'm going to go on from there. Alrighty, so you can see I've calculated my A, B, and R values. So I've now got my equation, y equals A plus BX. So it's going to be y is equal to 48.9 minus 0.6x. And with an R value of negative 0.91, that means that we've got a strong correlation and negative correlation. So we're all good for that. Let's have a look at B. So B, comment on the suitability of the model in terms of linearity and strength. So linearity, I would say that it's looking quite linear. You can imagine drawing a straight line in. You could obviously check this further by doing a residual plot, but even a line of best fit by eye, you can pretty well see that in terms of linearity, it is going to be linear. And the other part was to do with strength. Well, the strength's quite easy to work out because we know that it is strong based on the R value from up here. It's 0.91, which is strong. But the other thing that we usually want to say, but in this case it's not asking for the direction, but it is also negative. it is going down to the right, and r is negative. So we can definitely see that it is certainly a negative correlation. Alrighty, let's go on to C. C is asking us to predict. So Sydney has a latitude of 33.9 degrees south, and Townsville 19.3 degrees south. For which two of the cities would the model predict the average maximum temperature for February more reliably? Well, so this comes down to which one is going to be more accurate. Now, we didn't talk about it last time, but there's a danger between extrapolation and interpolation. When we extrapolate, we make predictions outside of what our data already tells us. So we're looking outside of it. If we go back to the example we did a little while ago, we only have data from here to here. So when I try to predict outside of there, I don't know whether it's going to suddenly slope up or whether it slows down or what happens. Anything could happen. We don't have the data to actually know for sure which way is it going to go. And so we then have to base our decision off which is better. Well, it turns out that if we have a choice, this is for C, and I'm just going to make a little note off to the side over here. Interpolation is more reliable than extrapolation. And in fact, that's going to be my argument for why I'm going to say that Sydney is going to be easier to predict than Townsville. We don't have anywhere as far north or further north than Townsville, for example, Cairns or Darwin. So we are basing our answer for Townsville on a worse answer. So Sydney will have a better prediction and then why? Because we will be interpolating. Which is just the verb version of interpolation. Okay? So that's for CI. Now for CII, we want to actually predict the average temperature for February in each city. So we know that for Sydney, we've got that X is equal to, 33.9. And for Townsville, we've got X is equal to 19.3. So now we're just going to substitute both of these into our line of best fit equation. So Y is equal to 48.9 minus 0.6 times 33.9. And that gives us, and we get 28.56, which I'm going to round up to 6 due to everything else being to one decimal place. And I'm going to repeat the process now for Townsville. So Y equals 48.9 minus 0.6 times 19.3. And in this case, I get 37.32, which I'm going to round to 37.3. And there we go. So there's our two predictions for II. And the last part, given that the average maximum February temperatures are Sydney 26.3 degrees and Townsville 31.1 degrees, comment on the accuracy of the residuals. Alrighty. So remember, we've now just been told that our predictions were this, but the Y actuals for Sydney is 26.3. And the Y actual for Townsville is equal to 31.1. So the residual is YA minus YP. And in this case, we're going to get 26.3 minus 28.6. So the residual is going to be negative 2.3. And the residual for Townsville, YA minus YP, is going to be 31.1 minus 37.3. And we're going to see that it's going to be quite a bit further off than the real one. So you can see once again how ineffectual, also how misleading extrapolations can be. Townsville was the extrapolation, Sydney was the interpolation, and we can see that the interpolation was only 2.3 degrees off, whereas the extrapolation was 6.2 degrees off as well. So Sydney's prediction was 2.3 degrees Celsius higher than it should have been. Higher than the actual, while Townsville prediction was far less accurate being more than 2 degrees over over the actual. Alrighty. So that is a little bit of practice on that. I'll see you in the next one. Goodbye.